right, this video is for lesson 5.2, Extrema on an interval. But I want to start with a little warm-up. So I'm going to ask you to read the examples you see on the screen, pause the video, and give these two a try. These two examples, or I should say one example with a couple parts, is just going to make sure that we set the stage for the proper vocabulary as we continue talking about extrema. So pause the video, give these a try. If you're coming back, you're checking your work, and you're realizing we need to know the difference between relative extrema versus absolute extrema. So in part A, given the function g of x shown at the right, state the relative extrema. Relative extrema are going to be the extreme highs and lows in the local neighborhood. So I actually color code these on your picture. A relative extrema could be the point -3/8. When we report the extrema, we really report the y value. So -8. I might write instead, this has a relative minimum at -8. We have another relative minimum at the y value of 0, the ordered pair 4, 0. And we have a relative maximum at the ordered pair 2, 2. So a y value of 2. So again, when we report extrema, we're reporting the y values, but the x values really tell us the location of them as well. So just keep in mind, in some instances, you'll be asked to report the location, so a point. You'll be asked to identify what x value they occur at, or you'll be asked to report the extrema, which would be the y value. Okay, so then switching gears, considering the domain, considering that this function is infinite, what are the absolute extrema of the function? So we're talking about absolute extrema. We're talking about the absolute highest and lowest the function can go on the range, or on the y-axis. So let's first talk about absolute maximum. Because this function continues to rise infinitely, there is no absolute max. Because every time you try to tell me, well, this point right here in blue is the absolute maximum, I'll be able to tell you a point higher because the function's range is infinite. So what is the absolute minimum? That is going to be the lowest possible point in the range of the function, which is that minimum at -3, -8. So it has an absolute minimum at -3, -8, and its absolute minimum value was -8. Okay, concepts that you should have seen before, just reviewing the vocabulary, because we're going to use them a lot in the next few sections. So 5.2 is all about identifying extrema on an interval. Really what we're studying in this lesson is a very important theorem called the extreme value theorem. So maximum and minimum values of a function are called extreme values, or extrema. Extremum would be the singular term. The process used to finding them is referred to optimization. We're going to see this idea later on again. We talked about optimization problems in, I think, section 5.6. There will be times when we want to find the max and the min for x on the entire domain, and at other times on a particular interval. So in this lesson, we will learn how to use calculus to find extrema rather than calculator. You notice highlighted and kind of highlighted, color might be faint to see, and then starred is really the question that we're answering today. What conditions would be necessary in order to have both an absolute maximum and an absolute minimum? So answering that question, we'll need the extreme value theorem. The extreme value theorem says that as long as f is continuous on a closed interval a to b, then f has both a maximum value and a minimum value on the interval. Big pieces of the conditions of this theorem is that the function has to be continuous and closed when we're talking about our interval. So if it's not a closed interval, EBT does not apply. If it's not continuous, EBT cannot apply. Meaning, on non-continuous functions, or functions that, or instances where we're not looking at a closed interval, we're looking at an open interval, we cannot guarantee that there's both a maximum and a minimum value. It might have one, it might have the other. So extreme values can occur at interior points or endpoints of a closed interval. A function may have both max and min values, either a max or a min, or no extrema at all. So let's explore some examples. Example 4, for each graph, explicitly state whether the hypothesis of the EBT fails on the interval or not. Then determine, or I should say where, doesn't say whether or not. So where does it fail? Meaning all 4 of these examples do fail the EBT. Tell us where and how. Then determine if the function has an extrema on the interval. So that second part is going to feel a lot like the warm-up we just did. Okay, example A. Again, those 2 conditions. We want to look for continuity. And we want to make sure that we're looking at a closed interval. Or more specifically, it's continuous on the closed interval. So on our first function A, right away we can see that this is not continuous. From 0 to 3, we have a jump discontinuity. And so it fails because f is not continuous on 0 to 3. There's a jump discontinuity. This function does have an absolute minimum at its endpoint at 0. So we're just going to say at x equals 0. Guessing the extreme value would be roughly a half. This function does have an absolute maximum, this point here, at an x value of 1. Example B, very similar to A. You notice that there's still a jump discontinuity on our closed interval 0 to 3. So it's not continuous. EBT cannot apply. Okay. This function, we talk about minimums first. This function does not have an absolute minimum. And this is kind of the interesting one because really the lowest point is at that open value. Some of you might say, well, it's going to hit an absolute minimum right next to it. But if you think about what it means right here, this function continuously approaches that x value of about 1.5 and that y value of 1. But it's never going to be exactly equal to an x of 1.5 or a y of 1. It's going to get infinitely close to it. Imagine that there's like this continuum there, that line that continuously stretches towards that open circle. It never ends. It's a hard and weird concept for us to imagine, but it's true. There's no absolute minimum because it's going to continually or infinitely get close to that open point. This function does have an absolute maximum. We've got a filled-in circle up there, and that occurs at an x value of 0. Okay, example C. How or where does this function fail the EVT, the extreme value theorem? Well, it's not continuous on my closed interval. Right. We've got an open circle. Closed means it's at exactly 0. And so since we have an open circle at 0, that by definition is not closed. We would say it's continuous on 0 to 3, but not on that closed interval. So it's still the continuity piece that's failing. Okay, this one has no extrema. You talk about an absolute minimum, this function is continuous. It's going to keep going, so there's no absolute minimum. And then for the same reason, example B, this point appears to be the highest, but because it's an open circle, it's going to infinitely increase, infinitely approach that. And so we're going to continuously have higher and higher y values to report. Can't arrive at a single absolute maximum. Okay, D, really should have copied the same explanation from C. I think I worded this one a little bit different. It fails because it's still, yet again, not continuous on the closed interval. It's not closed. It's open. Okay? Not closed. This one does have an absolute maximum and an absolute minimum. Got some solid circles. Here's my absolute minimum at an x value of 2. And an absolute max at x, it's not quite 1. So if you want to say 1, you can, but it's probably a little closer to like maybe 1.2, somewhere in there. Okay, so the extreme value theorem gives us the knowledge of when extrema occur, but how will we find them algebraically when given an equation only, without the benefit of the graph, right? So far, graphically, I've asked you to assess when EVT fails, and then graphically identify the extrema. So just like that question states, how do we do this algebraically, given the equation and no graph? So our next question should be, how can we identify all the values of x where the extreme values occur? So our next few examples will give you some experience answering that question. For each of the functions below, justify and explain why the extreme values theorem can be applied or why it does not apply on the given interval. So here we need to stretch into our knowledge of algebraic functions, so parent functions. What do we know about them? What do we know about their shapes? Where are they going to fail to exist? Where might they have vertical or horizontal asymptotes? So example A, we see this rational function. Right away, we should go, okay, there's a problem because I know that this function cannot exist when x equals 2. If x equals 2 in this function, my denominator would be 0. Undefined value when we divide by 0. So simply because it cannot exist at 2, and I notice our interval, our closed interval is -4 to 4, because 2 lies in that interval, it's not continuous on the closed interval. EVT must fail. The biggest condition you have to make sure you're meeting to apply this theorem is that it's continuous. So again, EVT does not apply on our closed interval -4 to 4 because if f of x is not continuous at x equals 2, which is contained in the interval. Example B. Again, we need to look into our parent function. This is a exponential function. This is with base e at that. You can remember what these look like. They are continuous, but they look a little bit different. Again, it's an exponential function, so they are continuous everywhere. I wish you guys were in my classroom so you could see my parent function posters. Exponential functions either are exponential growth, they approach a horizontal asymptote, or they are exponential decay. They still approach a horizontal asymptote. So what might scare you with this one is that it's base e. Replace that with about 2.718 or about 3. That's really saying 3 to a power of x minus 2. Don't get yourself scared by the letter e or the number e. So since we know this function is continuous everywhere, there's no restrictions on the continuity of it. It must work with EVT. G of x is continuous for all all real, therefore EBT must apply on this closed interval, -5 to 5. All right, last example in this little chunk. H of x, it's a product of our linear function and our square root function. So thinking about what we know in this one, think about where the function would fail to exist. Right away, we're trying to take a square root of a number. That radicand that I just circled, x plus 2, has to stay positive. So this function exists only if x is greater than or equal to -2. Think about it again, if x was -3, you'd be trying to take the square root of a negative number, which does not exist in our real numbers. It's a complex number, but that's not a real number. So looking at where it's going to be continuous, it's going to be continuous as long as x is equal to or bigger than -2. Compare it with your interval. Because we're looking at values smaller than -2, EBD cannot apply. Since h of x is only continuous for values where x is greater than or equal to -2, EBT does not apply on our interval. Now, if I were to change this problem, and if I said from -2 to 6, then we would get to say EBT applies. It's continuous on that closed interval, -2 to 6. So just a point worth clarifying there. Okay, so let's get into, we kind of picked apart the theorem a little bit. When does it fail to exist? When can it exist? Or when does it apply, I should say. So now we get to actually use it. All right, so a little vocabulary and a little extra information before we start to use the EBT a little bit. Critical numbers, we need to talk about those first. Our critical number or value of a function, f, is an x value, some x equals c, in the domain of f such that either the derivative at c is 0 or the derivative at c does not exist. So really it's where the tangent line if it's equal to 0, then we know our tangent line is horizontal. Or at the endpoints where they wouldn't exist. So I guess I could say it a little bit better, but I'm just going to write it on the endpoint. Because where the derivative is not going to exist, of course that's going to be at like non-differentiable values. Think about discontinuities. But think about the endpoints. You know, if I draw a function, something like this, a very good one to use an example because I have a point right there. It's not, the derivative is not going to exist at my endpoints because you think graphically, trying to draw a tangent here, there'd be an infinite number of ways to touch at one point, right? So it doesn't exist. Here's an example where it would be a horizontal tangent. The way that I drew this one in the next kind of little corner, this looks like a sharp corner, so that would be non-differentiable there as well. Okay. But, okay, so a critical number is where the derivative is 0 or doesn't exist. We call this value at x the critical value or the critical point. Okay, so some theorems to take note of here. The relative and local extrema can only occur at critical value in the open interval. Again, it has to be an open interval. If it's not an open interval, if it's closed, then we're talking about absolute. So you see the difference here as well. Absolute or global extrema must occur at a critical number or at an endpoint on the interval. So if you're being asked to find a relative, you know that you're looking at the critical values on the open interval. If you're looking for absolute or global, you can look at the critical number or at the endpoint. Never look for a relative at the endpoint. So now we need to put these ideas together with a little direct practice. We're going to use what's called the candidates test for finding extrema. very rarely would you ever be asked to, in a question, use the candidates test to find. So I don't think it's extremely important that you understand this test by name, but it is good to take note of the name so that if you hear it again, you know what it is. Have your calculators ready to help us with this. Find the absolute extrema of the function on the given interval, provided the EBT is applicable. If it is not applicable, justify why. So we want to find the absolute extrema. We know the absolute extrema can occur at critical values or endpoints. So first, we're going to find the critical values. We're going to find our derivative, and we're going to find where the derivative would fail to exist or where it is equal to 0. Okay. Find our derivative of our cubic function, 24x squared minus 6x plus 9. Let's set that equal to 0. And at the same time, I'm going to do a little factoring because I know I'm going to have to solve this. Factoring is a good way to try to solve it if it's factorable. Everything looks like it's divisible by 3. Okay, trying to factor next. You can use that AC method, or I just do guess and check. So feel free to pause and factor it on your own. I know this has to be 4x minus 3 and 2x plus 1. If I just double check that really quick, 4x and 2x makes x 8x squared. We get our negative 3. We get negative 6x plus 4, which is a negative 2 system. So I know I'm going to have zeros on this function, or solutions, where 4x minus 3 equals 0, or when x is 3/4, and when 2x plus 1 equals 0, or at x equals negative 1/2. Okay. So because they're the critical values, there should be horizontal tangents at those values, which means if you've got horizontal tangents, you should have an extrema, maximum or minimum. Okay. We have to figure out which one's which, and then figure out the maximum or minimum values. Okay. What I didn't even talk about really to get started was whether or not we can actually do this. So whether or not EBT is applicable. This function is a cubic function. It is continuous everywhere. Okay. So again, I modeled this poorly. I should have started, put a big number 1 by it. EBT applies since f of x is continuous on our closed interval negative 1 to 2. Okay, and you should just know that this is a polynomial function. It's continuous everywhere, therefore it'll be continuous on that closed interval. Okay, so again, I modeled that poorly. That's where you should start. Okay, so now that I've partway through that, I know my critical values are at 3/4 and negative 1/2. So now I'm going to try to figure out at 3/4, at an x value of 3/4, is that a maximum or a minimum? At negative 1/2, is that a maximum or minimum? And then what's happening at my endpoints as well? So the candidates test is really about making a table. Often you'll see the table rather than seeing, a traditional XY table where it's set up vertically. Oftentimes you'll see the candidates test written horizontally. I'm just going to follow that because that's what I've seen before as well. Okay, so I want to find out what's happening at my endpoints. First one was negative 1. Then at my first critical value, negative 1/2. My second critical value, 3/4. My other endpoint of 2. So just noticing I went in order from smallest to largest. Okay, here's where use your calculator. We want to figure out what's going at that function value. So I'm going to type in my function, not the derivative. I want my function. So 8x to the third minus 3x squared minus 9x. I'm sorry, this isn't typing correctly. because of my smartboard pen. Let's go back. Sorry guys, annoying to watch, deal with it. Okay, there we go, minus 9x. Hi. Finally, okay. So I like to enter the function in so then it's easier. So then I'm just gonna go to my regular calculate screen. I'm gonna go vars, yvars, function, choose y1, that's where I entered it. So I want to evaluate this at my first value, my endpoint of -1. It was 0, so I'll go record that in my table. I'm going to do the same thing, but change it to my -1/2. Same thing, but 3/4. And finally, my last endpoint at 2. Okay, so now using this table to organize our thinking, we can very clearly see that we have, again, these are the only 4 locations where our maximums or minimums can occur. So we very clearly see that because 2, the x value of 2 had the highest y value, that has to be our absolute max. And because at 3/4, that had your lowest y value in the table, that has to be your minimum. That's the candidates test, that's it. Okay, so we kind of review it. Does EVT apply? Check that first. If you don't check that, then you're going to go through all this work just to get incorrect assumptions, incorrect conclusions. So apply that first. Really, you're just looking, is it continuous on the interval? If it's continuous, then you must have an absolute max and a min. Okay. Then use your derivative to find your line or your locations where your tangent line is horizontal. So set your derivative to 0 and solve for x. Organize yourself with the candidates test. Make sure you include your endpoints and your critical numbers. Okay, I'm going to do 2 more examples of the same thing. It would be probably pretty helpful to see b because it's a trig function, and also very helpful to see d because it's a natural log function. Basically, I'm telling you, if you think you got it, be done watching the video. Otherwise, hang on and hear these out. So first, I want to find if EVT applies. Okay, I've got a sum of a linear function, which is continuous everywhere, and my sine function, which is continuous everywhere. So a sum of a difference of 2 continuous functions must be continuous. EVT must apply. Okay, find your derivative. 1 minus 2 cosine of x. Set your derivative equal to 0. So we're going to find where the cosine of x, you have to subtract 1, get -1, divide by -2, so you're looking at +1/2. So think back to that unit circle, where or what angles have a cosine value of 1/2. That occurs at pi/3 and 5π/3. So I'm going to get ready for my candidates test. To find where I have an absolute max and min. EVT says I should have both because it's a continuous on this interval. Remember to include your endpoints. So I'm going to look at 0, my first critical number at pi over 3, my second critical number at 5 pi over 3, and my last endpoint at 2 pi. Okay, use your calculator to evaluate. Again, the tedious part for me. Make this part simpler for you. So rather than entering everything in, I mean, I guess that's just as efficient. I like using this vars option. It feels like I have less to type. Make sure that you're in radian mode. Check, make sure I entered that correctly. Again, I'm not looking at my derivative. I'm not evaluating at my derivative. I'm evaluating my function. Where does my function have max or mins? Okay. Go to the regular calculate screen, go to vars, yvars, and choose the function you entered it in for, y1. So we're looking at 0. We're looking at pi over 3. We're looking at 5 pi over 3. And we're looking at 2 pi. Okay, you can record those values. At 0, it's 0, negative 0.685, 6.968, 6.283. So where do I have an absolute maximum? Look at your highest value. 5 pi over 3 would be your max. Your location of your max, so your maximum value would be 6.968. Your minimum value would be negative 0.685. Okay, the last one. Okay, first step, does EBT apply? The natural log of x squared minus 9. We must know about natural log functions. Again, here's where I wish you were in my classroom to see the posters. I'm just going to draw it really quick. Okay, the natural log of x is the inverse of e to the x. And so if e to the x has horizontal asymptotes, natural log functions have vertical, which means they fail to exist in the domain. Okay, the natural log function, the natural log of 1 is 0. It's going to go through 1, 0, and then it looks like this. It has a vertical asymptote at 0, meaning the natural log of 0 is undefined. Why is it undefined? This is really asking you e to what power is 0? Doesn't exist. So x, or I should say this value in here, cannot be equal to 0. Think about it. It's going to be equal to 0 when x equals 3. And, I'm sorry, I'm forgetting about my negative, when x equals negative 3, right? Because 3 squared is 9, and so is negative 3 squared. So, and it's not going to exist anywhere in between those, because we're going to have negative values as well. So, it's undefined from negative 3 to 3. But again, what I'm kind of skipping over yet talking about, so listen carefully, it can exist, or the natural log of 0 doesn't exist, so x can't be 3 or negative 3, but if you plug in a value in between, so let's say 0, you're going to get the natural log of negative 9. Think about what that means. That's asking you to find the power on e that will give you a negative number. that doesn't make sense. You can't take a positive value and raise it to a power and get a negative value out of it. That doesn't make sense. So as long as you have a negative number in here, and that natural log doesn't exist, and that happens from -3 to 3. So because our interval is -2 to 5, EVT does not apply. Sorry, my smartboard's having problems. That says on. There we go. That's simple. That's just like the examples we did previously. EVT doesn't apply. So we will not move on to the candidates test to find the absolute maximums or minimums. At this point, we don't know if it's a minimum or a maximum. Finding the derivative, then things would be inconclusive. Done. Doesn't apply.